So we could have done the empirical formulas much earlier on in the whole worksheet, but because of the very last question, better to save it at this point, I think. Anyway, regular routine pattern for determining the empirical formulas of substances. You'll find more examples of this, and of course, in the A-level worksheet as well, because it does seem to be something that the A-level boards love to do. First question, straightforward question, but to emphasize where most of the empirical formula calculations come from, and that is the relationship between the mass percent of a given type of atom in a formula. So we got the whole formula, C2HBrClF3. What's the mass percent of carbon? Well, we've got 2 carbons, so 2 times 12 over the whole mass, so that's 2 carbons and a hydrogen and a bromine and a chlorine and 3 fluorines, as its percent times 100. 12.2%. We'll apply this in this next question, in which now I give you the mass composition, so that's the percent by mass, in other words this bit here, and we have to work backwards for it. C2, 62.58% carbon, 9.63% hydrogen, 27.79% oxygen. So anyway, I've sort of put all this together in one big table rather than revealing it bit by bit. Here's our percentages. So what we do is we say, well, let's imagine we have 100 grams. Well, in 100 grams, there would be 62.58 grams of carbon, 9.63 grams of hydrogen, 27.79 grams of oxygen. Convert those to moles, dividing, of course, by 12, by 1, and by 16. Now then we get, this is actually as a mole ratio, which could give us the formula, but we want to make it nice and pretty. So we divide by the smallest, which is 1.73. 5.22 divided by 1.73 is 3. 9.63 divided by 1.73 is 5.5, and then 1.73 divided by 1.73 is 1. Obviously this 5.5 sticks out like a sore thumb, so we want to get that ratio as a nice ratio. 0.5 is obviously a half, clear that by multiplying by 2, so we get 6, 11, 2, or in other words the empirical formula, 6 carbons, 11 hydrogens, 2 oxygens. Empirical formulas, CH2, its molar mass is 112 grams per mole. How many hydrogens are present in the molecular formula? Well, this is that next step from the empirical formula, relating it to the molecular formula, is the same relationship as between the mass of the empirical formula and the molar mass, which is, of course, the mass of the molecular formula. So the empirical formula goes to molecular formula by multiplying it by some whole number n. The empirical mass goes to the molar mass by multiplying by the same n. So CH2 is our empirical formula, which has an empirical mass of 14. The molar mass is 112, so we can just divide 112 by 14 to get n, which is 8. And so therefore the molecular formula is simply going to be the empirical formula times that same 8. So C8H16, or in other words, 16 hydrogens. Finally, one of the nastier types here. This is about as nasty as it gets in terms of now we're thinking about reactions in terms of what we're doing here. We're burning this compound, so all the carbon gets turned into CO2, all the hydrogen gets turned into water, and from that we can determine how much carbon we had, how much hydrogen we had, figure out how much oxygen we had using that, and then get the empirical formula. So, start off with the carbon. 18.94 grams of CO2 was made. Divide that by 44 grams per mole, and that tells us we have 0.4305 moles of CO2. And as all the carbon in this went into CO2, and that's 1 carbon in a CO2, that tells us we started with 0.4305 moles of carbon. So we can go right there, 0.4305 moles of carbon. All the hydrogen went into H2O. We have 7.749 grams of water. Divide that by 18. So we got 0.4305 moles of H2O. But of course there are 2 H's in an H2O, so we multiply that by 2 to get the moles of hydrogen, and 0.4305 times 2 is 0.861. So we know the moles, relative moles of carbon, relative moles of hydrogen, so we can get the carbon to hydrogen ratio. But now we need the oxygen, and to do that we have to go back quite a bit, because we know that we started with 12.915 grams that had carbon, hydrogen and oxygen. We know the moles of carbon we had, we know the moles of hydrogen we had. If we know moles of carbon, we can turn that back to grams of carbon. If we know moles of hydrogen, we can turn that back to grams of hydrogen, just using the molar mass. So 5.166 grams of this 12.915 grams was carbon, 0.861 grams was hydrogen, the rest was oxygen. So the oxygen is the 9.915 minus the carbon minus the hydrogen, which is 6.888 grams of oxygen. Now, of course, we have grams of oxygen. Turn that into moles of oxygen by dividing by 16. And now we have the mole ratios. Okay, we got the carbon moles from moles of carbon dioxide. We got the hydrogen moles from moles of water times 2. Put those together to get the grams of oxygen, thus the moles of oxygen. Now we just have to divide by the smallest number, which is 0.4305. 0.4305 divided by 0.4305 is 1. 0.861 divided by 0.4305 is 2. 0.4305 divided by 0.4305 is 1. So thus the ratio CH2O. More examples of this, as I said, will appear in the A-level stoichiometry worksheet.